Hello, welcome back to 14 Minesweeper variants. So, yeah, okay. Today I think we're going to be looking at what I think is the most interesting variant in the first 14, which happens to be letter E. And E in 14 Minesweeper variants 2 is called encrypted. And this one is special along with L because their puzzles come with a secondary board. So the rules, okay, I'm just gonna it is gonna be a variant showcase, I guess. I don't know if we're gonna do the rest, but in particular, the one I'm really excited to do is actually E and L because those have secondary boards. So let's look at the rules. Maybe I'll do like a size 5 puzzle just to get us going. Alright, the rules. Two encrypted rules are clues are encoded by letters. Each letter corresponds to a number and each number corresponds to a letter. So on the actual grid with Mines itself, instead of numerical clues, you have alphabetical clues, and each alphabet corresponds to one number. And this second sentence basically means that every letter is a different number and every number is used by a letter. So you have exactly 1 to 1 basically. And so it produces some very interesting deductions. If you don't know how Minesweeper originally works, it essentially states that well, not states, but essentially whatever number you have here, which I think actually is a different color. I don't know if this is a nice color scheme, but I just got it randomly chosen for me. Oh well. Each letter is a number, but whatever number it is, let's say this is a 3, for example. Now what that means is that in the up to 8 cells around it, in this case only 6, but up to 8 cells in the 8 cells around it, there will be a total of 3 mines. And in this case, as you can see here, very obviously the mines can only occupy these 3 spots. So they all have to be mines. And yeah, that's essentially how these letters work. But with encrypted, we actually don't know what number this is. This could be anywhere from 0 to 3. But here comes the first piece of logic. This value cannot be 4. And obviously, if it was 4, you wouldn't have enough space to put 4 mines. And so this can't be a 4. For similar reasons, this A can be 4 and the C can be 4. So A, C, and E can be 4. And since we know there is a 1 to 1 pairing, the only number that can be 4 is in fact a D. So D is 4. Which is correct. If it were wrong, I would have been marked wrong, but it is correct. Okay. So now, well, if D was 4, then the second piece of logic is that even if you had put as many mines outside of E's range as possible, you would still have to put at least 2 mines inside, right? Because if you had less than 2 mines inside, then this 4 can never be accomplished. And so that means that E can never be less than 2, so it's at least 2. And so E cannot be 1 or 0. That really isn't much, but maybe something else will help us. Perhaps a C. I think C is pretty similar actually because the 4, if you rotated this, yeah, because of the quote-unquote diagonal symmetry here along this line, you can do the same thing for the 4. Even if you put mines outside of C's range as much as possible, C would have to be at least 2 because you would have to have at least 2 mines to fulfill the 4. And so C once again can't be less than 2. And that leaves E and C to be 2 and 3. And because it's a 1 to 1 pairing, nothing else can be 2 and 3. And so that means A is either a 1 or a 0, and so is B. And so this is either a 1 or a 0. This is either a 2 or a 3. And I think that does help us do something when matching them together about this line. Because they share cells, which is very interesting, I suppose. In Minesweeper, always sharing cells is interesting. But I guess more specifically here, there is at most 1 in here because A is at most 1. But because C is at least 2, there must be at least 1 in here. Because otherwise, then you wouldn't have enough to put at least 2 into C's range. And so because there's at least 1 and at most 1 here, there must be exactly 1 mine in those cells. Because there is exactly 1 mine in those cells, we now know that A can no longer be 0, because there's already at least 1 mine here. Similarly, C can't be 3, because you can't have all 3 of these be mines, because there's only 1 mine in those 2 cells. And so we already get the fact that A is a 1 and C is a 2. And B and E follow very naturally, just B is 0 and E is 3. And now we can solve the Minesweeper as per usual. 3 is solvable. There is 1 mine here to complete the 4, which would then complete the 2. 2 here gives us a mine there. 3 here gives us a mine in one of those cells. And this 4 now can be completed because there is one mine in those cells. The rest must all be mines to fulfill the 4. Because we know there's one mine here, this one is complete, so that is not a mine. Therefore, by this 4, this is a mine. Therefore, that's not a mine. By this 3, we're done. That's not a mine. 3 here is complete, so that's not a mine. Therefore, that is a mine. And because there are 2 mines remaining and 2 cells remaining, both of them have to be mines. So yeah, the final part was just a very quick dash to complete the Minesweeper. But that part is all very standard, the Minesweeper part. The special part was the encrypted, which I think has very pretty logic. So that's why I wanted to showcase it. 5x5. This actually was a pretty challenging one for a 5x5, I think. Yeah, the connecting the E, A, and C all together. Pretty cool. But as we go up, the logic will just get a lot more complicated. So let's see how we can do this, shall we? Alright. So now we have a 6x6. So our maximum value is actually up to 5. So 0 to 5. The first thing I see is the B and the B. This is very similar to having 2 values that are the same touching a wall here. If I had 2 and 2 here, then, you know, by regular Minesweeper, you can say that there are 2 mines in here. Therefore, because that fulfills this 2, there'll be no mines in these 3 cells. The same thing happens with this B over here, because the same thing will happen with whatever number you put in. So even if B was any value you had, the same still applies where all 3 of these are non-mines. Another B, okay. Well, this B is pretty obviously no longer a 2 and above, so we can mark that off. And I don't know, there's just a lot of letters here. So, well, F follows the same structure, right? F can no longer be 2 and above, which gives us the fact that B and F are 0 and 1 respectively. That means no other letter can be 0 or 1 because of this 1-to-1 pairing over here. C is pretty interesting because C only sees 3 cells. So C can no longer be above 3, meaning C is actually just 2 or 3. Any letters that follow that pattern? No. I think A is kind of close, but not really. D could be up to 5, yeah. So, nothing really much there. I think we do use every letter in this puzzle though. There are some puzzles that don't use every letter, and in those cases, something special will happen at the end. Alright, we know B and F are 0 and 1. Maybe the house is the A here. Yes, I think the A... Yes, because B can no longer be more than 1, you cannot have both of these be mines because B can't be 2. Therefore, this A can't be as large as a 4. Once again, because if it was a 4, the only way to do it will be to violate B, because B again can't be greater than 1. So A can't be greater than 4, and therefore once again A is actually only 2 or 3. Which gives us another pair. A and C are 2 and 3, so D and E cannot have that. And your final pair will be D is 4 or 5 and E is 4 or 5. Well, this E very clearly can't be a 5 because there's only 4 cells around it, and so E is actually a 4. D must therefore be a 5. This 4 is just complete. C could still be a 2. Or could it? I think C has to be a... does it? Yeah, C has to be a 3 and B has to be a 1. And this 4 actually pushes a lot of things up because it sees 5 cells total. It requires one of these to be empty, because if both of these were mines, they would break B, because B cannot be greater than 2. Therefore, one of these have to be empty, and therefore to fulfill 4, because one of these have to be empty, you would have to have mines here, and as many mines as possible in this cell. So you must have the maximum allowed to fulfill the 4, and by hitting the maximum, you cause C to be exactly 3, and you cause B to be exactly 1, because it cannot be any higher. And so I think by this logic, we can say that C is a 3, B is a 1, and therefore A is 2 and F is 0. And we can use our previous logic and state that there is one mine here, there is one mine here, and because of this one seeing one mine here, there is no mine there. Okay, well, that was a mouthful. This 0 means that's not a mine, this 1 is complete, this 2 is complete, this 4 can be completed, and I think at this point it is just regular Minesweeper. One mine here implies that there is a mine there. 3 and 5, I don't see anything yet. This is just regular Minesweeper, right? Yeah. Is it this? Right, because of this 2, there can only be one mine here maximum, and so the 5 requires mines here, here, and here to fulfill it. Therefore, this isn't a mine, and this 3 is also complete, so that isn't a mine. This 2 sees one mine here and one mine here, so this isn't a mine. 1 is complete, therefore 2 is here. This 2 is complete. 1, well, there are 2 mines remaining in 2 cells, so both of them are mines. Cool. Okay. Well, yeah, that's encrypted for you. Pretty sick. Variant. I love the logic so much. All right, let's keep going because we can't go any further actually. We have to do all three. All right. So C and C once again following the same logic. Those two can be mines. Geez, that's a lot of C's. Okay. Well, let's see. Well, this C and this C follow the exact same logic, but so those are all non-mines. C, well, we know now C that it just can't be greater than 2, so we can mark that off. A can't be greater than 3, so let's mark that off. B also can't be greater than 2 actually, so let's mark that off. D and E do not follow that. Yeah. I wonder though. We can also use comparisons. Because C sees whatever is here, and D sees whatever is in here plus whatever is in here, D we know has to be at least greater than C. And it can't be equal to C because we know each letter corresponds to a different number. So D has to be larger than C, definitely, and therefore D just can't be 0. I mean, D can only be 2 more than C maximum, so D really can't be any greater than 4, because C can't be more than 2, so D really can't be a 5. Oh, and well, I guess by this row over here, the only thing that can be a 5 is E. So that's 5. Interesting. So now B might be interesting, seeing that it's touching the 5. Or maybe it's A. Yeah, well, because of the 5, we know that even if we fill everything outside of A's range, there has to be at least one mine here, which would cause A to be at least 1, so A cannot be 0 anymore. Do we have any way of, like, I don't know, telling that? Yes, B similarly, even if we put everything out of B's range, there must be at least one mine here. So again, B is at least 1. B at least 1. Does that help? We have C and F. We haven't seen F yet. Have we seen E? Yeah, E is just 5. Okay, so this is again one of those where we have to use basically every letter except 1, but that doesn't really matter. C being 0 is interesting. Yeah, C also has to be at least 1 because the 5 here, even if everything was outside of C's range, has to have at least one mine here. So C again cannot be 0, and so F is the one that has to be a 0, even though there's no F here. Well, by this row, the only thing that can be a 4 is a D, so D is now 4. A is now 3 by the same logic. So yes. Okay, I think we can say that C is definitely just a 2, because 4 is this plus this, and since 4 has to be at most 2 more than whatever C is, C can't be 1 because you can't put 3 mines in the extra area, so C has to be just a 2 and B has to be a 1. So now we can solve the puzzle like regular Minesweeper. Those are both mines. 2 is complete, 2 is complete, 3 can be completed. 1 here implies that the rest of them have to be mines, so for the 5. This one is complete, therefore this is a mine. 2 means 1 mine here, and this 2 means, oh no, sorry, this 2 is complete. I didn't see those 2 mines, so those are all non-mines. 4 is complete, 2 is therefore complete, this 2 is complete, and 1 mine remaining, so it goes there. Cool, very nice. Mines like to form all these weird shapes. I don't know if like that's usual. Keep seeing these shapes form up in like encrypted. It's not like a thing, right? Oh wow, it's a lot of E's. Okay, well, let's do this final one before we move to 7x7s. 6x10. I just realized this thing is 6x12. I mean, that is true, it is 6x12, but it could be just be 6x6, but alright. Okay, let's start with E first. I mean, as you can see by this E cannot be greater than 1, so that already gives us quite something to work with. We also know that because of these 2 E's, by that logic, none of those can be mines. Same here, none of those can be mines. That's a lot of E's. And EA, I guess. Again, A has to be greater than E, and because A can't be equal to E, A has to be at least 1 more. And because it has to be at least 1 more, this has to be a mine. Also, because A has to be greater than E, A can't be 0. Similarly, B can't be 0. We know that A is exactly 1 more than E because of this singular mine. Therefore, B can't be 1 more than E because B would then be equal to A, which is interesting, I guess. Therefore, B has to be at least 2 more than E, which is kind of cool. So that's also a mine. And because B is 2 more than E, B can't be a 1 either. Oh, wow. Alright. F can't be 5, I guess. A actually can't be greater than 3, so A can't be 4 or 5. E can be 0, I just realized. Yes, E can be 0. Well, yeah, because B has to be exactly 2 more than E, and E can only be 0 or 1. B can only be 2 or 3, right? If you add 2 to 0 or 1, you only get 2 or 3. So B can only be 2 or 3, can't be 4 or 5. A also, since it must be 1 more than E, can only be 1 or 2, so it can't be 3. F, I think, yes, because of this row over here. F, nothing else can be 4, so F must be 4, and therefore all of these are mines. This B is already 3, so B is already at least 3, and B can't be any greater than 3, so B is just 3 exactly. And therefore this is complete, so none of those are mines. That's a mine, therefore. Well, because we know B is 2 more than E, and A is 1 more than E, A must be 1 less than B by that, simple math. So A just is a 2, and therefore E just is a 1. Cool, that leaves C and D to be 0 and 5, which is a huge difference. But okay, let's solve the puzzle. This has to be a mine, that's not a mine. 3 is complete. This 1 means that's a mine. 3 means that's not a mine. 3 here means one of those are mines. We can use that classic Minesweeper trick where this 2 sees at least 1 mine here. Because there can only be 1 mine here, so there's be at least 1 more mine there. That would complete the 3, so there is no mine here, and there is a mine here. 4. Well, there's 4 mines remaining, and we know that there's 1 mine here to complete the 4. Therefore, to complete this thing over here, the rest of these have to be mines. This 3 is complete, so that's not a mine. 3 here is complete, so that is not a mine, and therefore this 4 requires that 1 mine to fill it up. Yeah, and here we see something very interesting called a non-unique secondary board. And that is when you don't use 2 or more of the letters, and therefore they could be any number. Here, C could be 0 and D could be 5, and it wouldn't matter. Similarly, C could be 5 and D could be 0, and it wouldn't matter because they don't show up in the puzzle at all. So it doesn't matter what numbers they are. I don't know what happens if you actually try to solve them. Do you get it wrong? You do get it wrong. Wow. They don't even let you count things that are, like, incorrect. Yeah. Okay. Well, that's pretty interesting. Yeah. You can't actually mark these because you don't know. I mean, both are correct, but you don't know which one is the intended. I guess there's no right answer. There's no wrong answer either, but the fact there's no right answer probably explains why. Alright, cool. Next up, E7. Oof, we now have G and a total value of up to 6. Alright, well, let's start with A again. By simple logic, A can't be more than 2. D can't be more than 4. G can't be more than 5. C can't be more than 5. F can't be more than 4. So now we're only left with B and E. Well, E can't be more than 4 either, and so B must be a 6. C and G are the ones that are either 5 or something. Interesting. Okay, by this AD pair here, we know D is greater than A by at least 1. Doesn't have to be more than, doesn't have to be 2. Could be at least 1. But we all know that since D is greater than A, D can't be 0, and A can't be as large as a. A could be 2 if D was 4 or 3. So A could be 2, but D can't be 0 definitely. I don't know. C could be 5. F. Well. Alright, this might be where things get slightly challenging. I guess we now know that D is at least a 2. No, wait, C doesn't have to be 5. What am I saying? Either C or G is 5. Well, okay, if G was 5, then all of these are mines. That requires D to be at least 2, because there are already 2 mines near it. If C was 5, then even if you put as many things as possible outside of its range, you would still need 2 mines in the remaining cells to form a 5. So whichever was a 5, D is actually at least 2. Okay, so D is at least 2, which means D is not 1. I'm not sure how that was useful, but okay. D can be a 4, I guess. Could no, C can't be 0, right? C can't be 0 because you have to have some number of mines here for the D to be greater than A. So C just can't be 0. Can anything else be 0? Can E be 0? Can G be 0? No, for the similar reason. You must have mines here, which will fill up G. So G can't be 0. F. Could F be 0? Possibly, if you had a mine here and a mine here. Then A will be 1 and D will be 2. D will be 2. And then C could be a lot more than 2. G would never be 5 though. Okay. I mean, E, I think E could be 0. I haven't really checked it out yet. But yes, E could be 0. So I guess there really isn't much. Could A be 0? I think so. A could be 0. F could be 0. Yeah, F could be 0. We saw that. E again also could be 0. A could be 0. But this is never a mine, is it? If E, F, and A, whichever was 0, would always see that cell. So that can never be a mine. That's really helpful. And that's an E. So now E can't actually be greater than 1. Okay, cool. I'll take that. Cool. In fact, A also follows the same idea. A can't be greater than 1 either. So now E and A follow that same, like, they're a pair now, so nothing else can be 0 or 1. That's useful. Okay. And whatever E sees here, this E will also see, so none of those can be mines. A. Oh, well now, because this is seen by E, and A sees more of it, A must be more than E. And because they can't be the same value, A has to be exactly more than E. So A is a 1, E is a 0. 0 means that's not a mine, 1 means that is a mine. D could still be more. F, well, F can't be more than 2, so I think we've already found the value of F. F must be exactly 2 then, which means that both of those are mines. That's not a mine. D can't be 2, so D must be 3. This can't be more than 3 either. I guess that leaves C. Yeah, we haven't really seen that yet. But C can't be a 5 because of this C. So C must be 4, G must be 5. That means this 5 is complete, and we can solve regular Minesweeper. 4 is complete, this 4 is complete. This 2 means 1 mine here, that will complete this 4, so that's not a mine. 3 can be completed, so that's not a mine. 5 is complete. 2 here is complete, 2 here is complete. 2 here means 1 mine here, that will complete this one, which means none of those are mines. 4 can be completed. 1 is complete, 4 is complete, and 5 mines remaining, so those are all mines. Nice. Well, there you go. It's a pretty crazy logic actually. Wow, it started off really slow, but in the end it just got really fast. I think in the end it just becomes a regular Minesweeper puzzle, honestly. But yeah, I like the start of, like, it's so puzzly, like compared to the rest where it's Minesweeper. This one's a legitimate puzzle to solve. Because you gotta start off with nothing. Like this E and E here, none of those are mines, that's pretty obvious. Same for this C and C. Now we can work on the fact that E and C both can't be greater than 2, sorry. But even better, I think, is this. What? Oh, I clicked on D. Whoops. That was my bad. So C can't be more than 2 and E can't be more than 2. But D has no discernible value yet. Oh, okay, yes. C sees this. This is what C can see. No pun intended. This C also sees it. And so nothing else surrounded by C can be a mine, which gives us a lot of empties. Now G can't be more than 2. And that gives us a triple actually. In Sudoku, we call this a triple because there are 3 values taken by 3 letters. And so nothing else can take those values. And so actually we get this pretty cool looking pattern over here. Now F must be more than this value, but can't be a 6 because you only see 5 cells. B and A can still both be 6 though, so we don't know. We've also seen every letter already, right? Except D. We haven't seen D yet. Okay. Well, because of this G, whatever this G sees will be seen by this G, so this can't be a mine. Now meaning that, F cannot be greater than 5. Cannot be 5. It only sees 4. Also means from this A that F must be greater than A. And that's only possible if F was a 4 and A was a 3. So we have those. This 3 is complete. This 4 is complete. G must be at least 1, so G can't be a 0. Okay. I think B can't be a 6 anymore because of this 3. Even, yeah. So B can't be a 6 because putting a 6 here would require all these to be mines, and that will break this 3. So B can't be 6, meaning D will be 6 and B will be 5. And this 5-3 pair does help us because even if you put all the mines in this range, the 5 would still need 2 more mines to help it. And this 3 would be complete with 3 mines here, so none of those are mines. We got E now, which we haven't figured out the value of yet. Well, because of this 3, even if there were 2 mines here, there would be at least 1 mine here. So E now can't be a 0, which means C is a 0. That helps. I'm tempted to say that, yeah, E is a 2 actually, because of this 5. Even if you put a mine here, there must be at least 2 mines in this area, which means that E cannot be a 1. So E must be 2. G must therefore be 1, which means that's not a mine. Those 2 are mines. And we have finished the puzzle element. Let's solve Minesweeper. 2 and a 5 pair means that this has to be a mine. And there are 2 mines here, so those 2 are empty. 3 is complete. 3 here is complete. 2 is complete. 5 is complete. And 5 mines remaining. Those are all mines. Nice. Yeah, alright. Oh, this is so cool. Keep wanting to do this over and over again. Alright, C and C, very easy, those are mines. Lots of C's here. E must be greater than C. And so, well, firstly, C can't be more than 2, so that already helps. But E must be greater than C, but E can't be greater than 3. So E can't be 4, 5, or 6, but E can't be 0 either. Because it must be greater than C. Another C here, actually. Not sure if that is useful. C is pretty small though. Okay, but C could be 2 though, and E could be 3. So technically all of these could be mines, I think. So D could be as high as a 6. Yeah, that's valid, that's possible. I imagine C can't be 0. Because if C was 0, then those are non-mines. This C dictates that that's not a mine either. And therefore E will also be a 0, which is impossible, so C can't be 0. E must be greater than C, so E can't be a 1. In fact, E is greater than C, so that's a mine. Okay, that probably is way easier in proving that C is not 0. If C was 1, oh yeah, then A will be 2, because you can do this. If C was 2 though, yeah, then A could be 3, E could be 3. So this works. Could this ever be a non-mine? If this was empty, then... well, C can't be 0, so C has to be a 1. But this is paradoxical, I think. If this is empty, then the C must be at least a 1, because it already sees 1. But putting a mine here increases this C. So now this C is a 2, but this C is a 1, and that breaks. So now this can't be a non-mine, so it is a mine. That still doesn't tell us anything, I think. Because this could be empty, or it could be a mine. Both work. But what about this? Ooh, interesting. I think I started to see a pattern here about things outside of this C's range. If this was a non-mine, then this C needs to have at least 1 mine here, but doing so would increase this C, and you would get something like a 2 here and a 1 here, which also breaks. And so by that logic, this can't be a mine, this can't be a non-mine either, so it's also a mine. Okay, I don't know how that's useful. Really not sure how that's useful. Whatever's here... well, whatever is here will be seen by both this C and this C, and therefore adding the 1 on each C will give you the total number of mines, the value of C basically. And so whatever this C will see is also seen by this C in this region, meaning that it cannot see any more mines. So none of these are mine. I misclicked. Sorry, let me just quickly get back to all of this. Again, whatever this C sees over here will be seen by this C in here. So C can't really see any more mines, so none of those are mines. Cool, okay. Oh my goodness, okay, what did I have to do? C can't be greater than 2. E can't be greater than 4. E can't be a 0, C can't be a 0. And E can't be a 1 because E must be greater than C. Cool. Yeah, we already know E is at least 2. D now can't be a 6, so I guess we can have that. This C might be interesting. I suppose the E's might be useful in telling us something. It's entirely possible that both of these are empty though. Well, we know C is at least a 1. How's that useful? Not sure. It would be really cool if our puzzle only had 3 letters in it. Wonder if, yeah, maybe like some special puzzles do that. Okay, well, whatever this thing sees here. Okay. E must see 1 more for the C, and 1 more for the E's extra, because E must see 1 more than C. So E must see at least 2 mines here. I think that's what it means. Yes, E must see at least 2 mines there. And that would necessarily force at least 1 mine into here. So this C already sees 1. Does this E follow the same thing? There could be no mines here, I think. I think this could happen. Like something like this could happen. So I guess that's something. Okay. Can I confidently say there's 2 mines here though? I think so, yes. 1 more from the C and 1 more from the E's extra 1. Yes, I can confidently say there's 2 mines there. This E, no idea. This E, also no idea. Okay. Maybe this D is useful finally. Just kidding. I don't think so. There's an empty cell that isn't seen by anything else that could give it a lot of leeway. Okay. Well, suppose what? Suppose this was empty, I guess. Because of this E, because of these 2 mines and there only being 1 mine around this C, that mine would necessarily be here, giving you empty cells here, here, and here. E now seeing at least 2 has to have a mine there. Because there are exactly 1 mine there because E will see exactly 2. That's one case. What is the other case? The other case is if there was in fact a mine here. Oh. If there was in fact a mine here. Now E will be a 3. Or would it be a 3? Yes, it will be a 3. And because it is a 3, this E must have a mine here. So I'm pretty sure it's either no mines here or 1 mine here. Which should therefore indicate that that's not a mine. Oh, indeed. Indeed true. Okay. I will take that logic with me. This E. Well, whatever's in here, E will see that. E will see this 1 from the C. Will it also need to see 1 more extra? Yes, because this is whatever C will see from this C over here. And E needs to see exactly 1 extra. So there's 1 mine here. Does that give us a 1-2 pair? It does actually. Wow. In Minesweeper, a classic 1-2 pair refers to this kind of scenario. We have 4 cells and a group of them are 2 and a group of them are 1. Indicates that because there's already at least 1 mine here, there can't be a mine there. So hopefully, if my logic was right, there is no mine here. And there is exactly 1 mine here. Yes, alright, it was in fact a 1-2 pair. Now C, well, we already know. Now, what do we know? I don't know what we know. So I guess not. Okay. Now, this C is probably of importance somewhat. Is it? Maybe. I mean, E will always see 1 more than C, right? So do these form a pair? I think this has to be a mine. Because E will see 1 more than C, right? And if C, well, taking away this shared region, I should use probably a different color. This is a shared region between the C and the E here. They share this region. Now whatever's outside of here belongs purely to C, and whatever's in here belongs purely to E. And now E must see 1 more than C. Oh my gosh, I don't know what I'm saying. But that means that whatever's in here, E must see 1 more than that. And because there's already 1 mine outside here, E must see at least 1 more than this. So E has to see exactly 1 more. It has to see 2. So I'm pretty sure this is a mine. And because this is 2, C will see 1 less outside, which means none of those are mines. I'm pretty sure this is what happens. And let's check. Yes, alright, and we have F. Alright, way to spoil the fun. I think we were doing well enough with just C and E. But alright, if you say so. Very cool logic over here. Again, we still don't know whether C and E are 2 and 3, but this has brought us a long way actually, so that's cool. F now. Well, F can't be a 6 either, so I guess there's that. F cannot be a 6. Is that useful? Well, F can't be a 0, we've seen that. D also can't be a 0. In fact, D can't be a 1 either, so there you go. E is, well, E could be 2, so you could have 2 mines there and there, so not really. F, well, this C, I don't know, do I have to be mines here? F could just be 1. Could it just be 1? F being 1 is very interesting. I don't think so. Yeah, F can't just be 1. Because if it was 1, I think it breaks. If f was 1, then it forces c to be a 2, which gives you a mine here. Now that forces e to be a 3, but this e is now broken because it can't see 3 mines. This is empty. So f can't be a 1. So f is at least a 2. Could f be a 5? I think we're going to slowly whittle down the options. Or at least could this be empty, I guess is the question. This forces e to be 2. And c to be 1. Oh, that breaks. Wow. This being empty breaks. Because if this was empty, then this e must see 2. It can't see anything less. But that causes this c to also see 2, which is also wrong. So yeah, both c and e can't be 2 because, well, firstly this e already sees 3, which breaks e on its own. So this can't be a non-mine, it is a mine. And therefore, finally, c is definitely just a 2. Okay. Therefore, e must be 3. And we have so much stuff to work with here. That's a mine. That's a mine. 3, 2 means 1 mine here, but I think we already knew that. F now can't be a 5, so F must be a 4, can't be any other value. And F is complete. A, well, A is just a 1, okay. Way to go to spoil the fun again. This really could just be a question mark, but I guess it isn't for some reason. 3. Wow, that's a lot of mines around that. This is also a 3, which gives us at least 1 mine here. Huh. Well, okay, well, from this grid over here, we see these exactly 5. So there you go. This 3, I actually have no idea. Yeah, there could be 1 or 2 mines here. I don't think it helps the 5 at all. Okay. This is just Minesweeper actually. I don't think we have anything else to do. B and G all feel like the parts of a non-unique solution. Yeah. Is it the mines remaining? I don't think it is. No, there's no way. We know there's 1 mine here. Does that help the 3? No, the mines could be anywhere else. 5? 3? No. There could be 1 mine. There's 1 mine here for this 3. 5, I guess not. 5, oh, 5 is just complete. What am I doing? These are all mines. The 5 already only sees 5 cells. Yeah. Alright, this 3 is complete. This 3 can be completed. This 3 is complete. 2, 4. This 2, 4 is similar to a 1, 2 pair, I think. 4 must see at least 1 mine here. Because even if you put 2 mines here, you still have to have put 1 mine in these cells. I'm sorry. That will complete the 2. So therefore these are both mines and that's not a mine. 1 is simple. That completes the 4. That completes the 3. 5 means 1 mine here, and with 3 mines remaining, 1 mine goes here. The remaining mines must go there. 3 is complete, and that completes the 5. There you go. Alright, finally 8x8s. Jeez. Okay. Hold on. Hey, wait a minute. Did you receive a call? Aw. Okay, well if you did, I'm so sorry. I missed it. I'm not paying attention to the music it's playing right now. I'm just assuming synthwave is going on in the background. Either way, let's go do the final boss. Yes, 7 total values. Oh my goodness, you could form molecular. Yeah, F and H and C and I guess B to some extent. You could definitely form molecular compounds with these letters. Oh my, the CCH thing. Oh, this reminds me of Soko Bond. Yeah, grid-based chemistry puzzle. Okay. Yeah, I wonder if Minesweeper will get chemistry update. I feel like eventually it has something to do with Minesweeper. I don't know. Because if you think about like revolving atoms as Minesweepers, I don't know. Alright, well let's just begin solving here. This 8x8 is really large. It's an 8x16 grid. And our total value can be anywhere from 0 to 7. Alright, let's begin. So, starting with the most obvious ones. H can be more than 2. So we already have a lot of things going on there. C can be more than 3. But in fact, C must be more than H because of this shared region thing. So that's a mine. And C must be more than H. Therefore, why did I break? Oh. Okay, well for some reason C is definitely just not 3. I don't really like that. I'm just going to purposefully say that I don't know if C can be 3 or not. Because in my eyes, I think C can be a 3. I don't see why it couldn't. I know C can't be a 0 though from here. Why can C not be a 3? Is it this? Or if C was a 3, would that break H? I think it would. This set over here. If C was a 3, then H must be a 2 because H can't be any bigger than a 3. So that breaks this C, which cannot be a 3 anymore. Okay, I guess by that logic, C can be a 3. Cool, that means H can be a 2 because H can be C or greater. There you go. Okay. I think this set is a lot more interesting than it looks though. A lot more interesting. Something about a lot of shared regions. In fact, H is entirely bounded between two C's. They whatever C sees is exactly in, you know, H exactly takes half of this C and half of this C. So it's kind of like, I don't know. I guess, okay, it's C is definitely just a 2, I think. Because, oh, this is exactly a mine, yeah. By similar logic, because whatever is here, H will see at least whatever is equal to it. C must see more than this, basically, because this is entirely contained within H. If C sees only this, then it implies that C is at least equal to or less than H, yeah. At most, sorry. Yeah, because H sees at least 0 more. So, having mines in here only implies C is less than or equal to H, which is definitely wrong. C is more than or equal to H. In fact, because C can't be equal to H, C is exactly more than H, which means this must be a mine. And also none of those can be mines. A. Okay, well, whatever C sees here, A sees exactly 1 more than that. So that must be a mine. And because of this, A must be at least 2 or 3. So that gives us 2 options again. Okay. F. F doesn't do much. Nope. Okay. I guess B now. Because H cannot be greater than 1, these can't both be mine, so let's be an empty here. B now can't take all of those cells, so B can't be a 7. Not really very helpful. F can't be a 7 either because it doesn't have 7 cells around it. Once again, not very helpful. Maybe the C helps because C can't be 2. Right, so this set can't have 2 mines in it. Can't have more than 2 mines in it. Similarly, this set can't have 2 mines in it. So I guess the maximum in this set would be a 4. If you have mines here, 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 and here. In fact, this C actually, this C already sees 1 here. So there can only be a maximum of 1 mine in here. Adding with the 2 mines for this C, you'd have only 3 in this set over here. Even if you did have an extra mine there, this F can only reach up to 4. So I think none of those are mines either. Alright, cool. Good idea. I hope. Okay. I mean, if C was a 1, that would be very interesting. F can't be 0. We can see that already. F can't be 0. Can B be 0? I think B could theoretically be a 0. If H was a 1, C was 2, A was a 3. Yeah, I don't see any reason why not. Sure. Okay. Can we rule out the fact? Well, F is at least equal to 1 already. What does that mean? Can I prove that F is greater than C? I think so, actually. Because C... Yeah, C can only ever see exactly 1 mine more than F, technically speaking, but without this region. So, okay, it's really hard to explain, but this is a shared region between C and F in this cell and this cell. If C had no mine here, then F would 100% see more, because F already sees 1 extra. However, if C sees 1 here, then F has to see 1 more, because F can't see an equal number of mines. So F has to have some number of mines here, and therefore F is definitely greater than C. In both cases. So F can't be 1. Okay. How is that useful? F can be 4, definitely. F can be like a pretty big number. F can be 2, I think. As long as you have an empty mine here and a mine here. Then F can be 2 if you put a mine in one of those cells. Does that break C though? 1 mine here gives you no mines there. Gives you 1 mine here. I think that might break A actually. No, it gives you. Oh, wait a minute. No mines here. Sorry, no mines there. No. This works. This works. 1 mine here plus 1 mine here. Yeah, this works. Okay, so F can in fact be 2. Interesting. Alright, what? Is this the first? Yeah, this is the first 8x8. This might be the only 8x8 we do, given we have so little time. We do, in fact, have a decently small amount of time left. Alright. Let's just quickly try to get through this one. I think B is important, but I can't tell why. I mean, if B were like a 2, it breaks a lot of stuff. Although it wouldn't really break a lot of stuff. Would it? If B was something like a 2, then C could be 1, A could be 3, H could be 0, F could be 4. That works, I think. I don't know if specific combinations don't work. Like if C was a 1, you could definitely just have something that looks like this. Yeah, that's possible. Actually, could C be 1? No, actually, wow. If C was 1, D can't be 4. Look at that. If C was a 1, none of those are mines. F by nature cannot be a 4 anymore. So I guess B can't be 2 then, because B being 2 would force C to be 1 and F to be 4. That's so random, but I guess that's true. Not really satisfied with that option. Okay. Well, if B was 1, C will be 2, A will be 3, F will be 4. I think that barely works out, because you'd have 1 mine here, here, and here. That would in fact barely work out. And then H would be 0, which is also possible. Would it be possible actually? No, look at that. This H being 0 breaks this C, which we know is 2. Huh. Oh, right, because, yes. Oh, wow, okay. So, because H equals 0, H equals 1, C equals 1, C equals... Because C has to be exactly 1 more than H, B can't be between that value. I think similarly for the B equals 2, a much more simpler idea would have been, because A is greater than C by exactly 1, B can't be in the middle, so B can't be a 2, because you then have A is 3 and C is 1, and that naturally breaks because we know C is exactly 1 more than, A is exactly 1 more than C. For the same reason, B equals 1 is not possible because it's in between 0, 1, and 2. And so putting it there would require C to be 2 and H to be 0, which we know is not possible. So B can't be 1. B, however, I think can be a 0. If you had H equals 1, C equals 2, A equals 3, F equals 4, I think that's possible. 3 doesn't lie in the middle of anything, I think. Unless you talk about A and F. But A and F can differ by 2 because you have a lot of space here for a buffer. So B can in fact be 3, I'm pretty sure. But there's no real reason I should try and evaluate that. Now B equals 0 does feel very suspicious to me. B equals 0 requires H to be 1. Actually, let's think about it. B equals 0. B equals 0, H equals 1, C equals 2, A equals 3, F equals 4. I think that breaks. Why? Because this C over here now needs to be 2, and therefore I have to have exactly 1 mine in here at least. Yes, and because F is 4, even with that mine in this area, must have a mine here, here, and here. And without that mine would just break. So it must have a mine here. And this mine over here breaks this B, because B we knew had to be 0, and that breaks. So B in fact cannot be 0, because if it was 0, it breaks itself. So B can't be 0. B is pretty large now. We still have a lot of letters that could be 0 though. But yeah, now B is pretty large. In fact, those letters could also be a 7. So, wow. Okay. Really not seeing it here, but we could probably work with it. B was like a 6. I guess if B was a 6, let's do more stuff. Because H can't be a 2, these can't both be mines. Therefore, for B to be a 6, this has to happen. H would automatically be a 1. C will be a 2, A will be a 3, B will be a 6. And how would that help? Or C being a 2 has to have a mine here and here. F I think would have to be a 4. C being a 2 puts a mine here and puts a mine here and here for the F. Yeah, okay, this could be a C, which gives us no mine there. No mine here, no mine here, no mine here. This works. This works, unfortunately. One mine here, C, this works. No mines here. Okay, maybe C and F still have some sort of relationship. Because... could there be a mine here? I think the answer is yes. If C was a 2 and F was a 3. That's the only way. If C was a 2, F was a 3, the only way... This is the only way it could happen. For there to be a mine here. What if there were a mine here? That this C is already a 2, which means that this can't be mine. F would now be at most a 4, but I already knew that. This, but F can no longer be a 4 actually. Oh, that breaks, I think. Yes, because this C cannot see a 3. So this F can't be a 4, because putting a 4 here will give us all these values. And so now F can't be a 2, can't be a 4, it must be a 3, and that breaks A, because A now has no option. Okay, so by random ass logic, I think I found the fact that this is not a mine. H, hey, there you go. Okay, this is probably helpful. H is 0 or 1. Does that break the fact that this can't be a mine? If you had a mine here, C is 2, H is 1. No mines here, no mines here. F is exactly 3, giving us this, giving us this. Oh, this still works somehow. Jeez, okay. This actually might be the valid answer. If H was a 0 though, then we know C is exactly 1. Which gives us a 1 mine in one of those cells. A... I don't know what A could... A has to be exactly 1 more, so A is in fact 2. F... Oh, C is 1, so F can no longer be a 4. So F is in fact 3, which gives us something that looks like this. Which is also possible actually. Wow, this is actually a valid scenario. Wait a minute, is it? No, it's not. No, it's not. No, it's not. If H was a 0, C is a 1, but that does mean that these are all non-mines. Yes, now A is a 2 because A is 1 more than C. And now F can't be 3 or 2. F can't be 4 definitely because F doesn't have enough cells. F can't be 3 because if it were 3, you break this C. And F can't be 2 because A is already 2. So that breaks. Meaning H can't be 0. Wow. Okay. So I guess, again, by long-winded logic, H is definitely just a 1. C is definitely just a 2, A is definitely just a 3, F is definitely just a 4. Cool. So now we have actual values, finally. That gives us some stuff to work with. There is 1 mine here, 1 mine here. 2 means something. 1 mine here. I think 2, 4 does work out. Yeah, 2, 4 does work out because there can only be 1 mine here. And even if 2 mines outside of its range, you will still have at least 1 mine here which will complete the 2. Therefore, none of these are mines and all of these are mines. Cool. 4 now is complete, 2 now is complete. Alright, we're getting through this. Finally. This can't be a mine. D. Oh my goodness. Well, D is no longer a 0. We got that. D is at least a 3, but in fact D is at least a 5, but can't be greater than 5 because you don't have that many empty cells, so D is exactly 5. B is therefore exactly 6. There you go. And because B is a 6, we've already seen there is exactly 1 mine here, therefore these are all mines. These are all non-mines. 3 is complete, 1 is complete. Okay. This EG combo is probably another case of unfilled things. Alright, this 2 is complete, this 1 can be completed. 3 is complete, 2 is complete, 2 is complete, 4 is complete. 1 can be completed? Yes. Alright, this 3 can be completed, 4 not yet. This 4 can be completed. 1 mine remaining has to be here, so none of these are mines. 6, well 6 already C6, so that's not a mine, therefore that's a mine. And there you go. Oh, and E and G again. We don't know which is which, so there you go. Okay, oh, this was incredibly fun actually, no matter how slow it got. I really enjoyed this, and hope you enjoyed this too. Yeah, so E is one of the coolest pieces of logic I've seen in this game. Another puzzle set that also uses double grids are Liar, but we'll see that in a future episode. Yeah, until then though, hope you enjoyed this video. See you guys next time. Bye bye.